So, I'm just gonna wait until some people join in. Yes, I type very fast. You'll definitely get a lot of that today, actually. Okay, so, plan for today, we're going to, so I wrote, the first couple pages yesterday while I was making sure I was still, on the ball. So we're going to go over some of these. You can ask questions about them, and this will be, I guess, sort of an introduction to all of this stuff that you've probably never seen before. You can stop and ask questions at any time also. So this is my third draft of Infinitesimal calculus of Dirichlet product, which is the research that I've been working on for about the last year or so. So starting out, we have, so far we just have the preliminary section. There's quite a lot here, actually. The preliminaries, the first 2 pages is very dense. So we'll just sort of go over that, and we'll look at, what are all of these objects, how do they work, and sort of what's known about these structures so far, or at least what we need to know before we can sort of get into it. Starting out, the structure of objects itself that we're studying is we're using this math blackboard bold A symbol, and it's just it's a function space. If one characterization is a function space from the natural numbers, that's the positive integers, into the complex numbers. Another way you can think of this is as a countable product of countably many copies of the complex plane, where the index of the dimensions is, again, the positive integers. So that's 2 possible characterizations. So it's a product of complex numbers. You can also think of it as a sequence space, so the set of all complex sequences. That's another way to think about it. So because the complex numbers is a field, one of the ways that we can think about this structure is as a vector space. So in the same way that you might have, r power, 1, 2, or 3, you can also have r power naturals n, which would be countably many products of real numbers. And here, instead of using the real numbers, we just have complex numbers. So one of the characterizations is that this can be thought of as a vector space. We can also think of it as a topological space. So the complex numbers have their own native topology, which is the same topology as the plane, the 2-dimensional plane. So the topology is how we figure out what limits are. So how do we take limits in this space? And so the topology is, we're just using the product topology. And so what that means is if we have a whole bunch of different objects in our space, our arithmetic function space, if we have a sequence of objects, we can take a limit of these in the same way that you would take a limit of functions. So when you think of them as functions, where the domain is the natural numbers, the limit is pointwise. So it's the topology of pointwise convergence. We'll get more into that as we go along. So we can think of it as a vector space. That's one characterization. We can also think about it as a topological space, because it's a product space. And both of these notions will be important to us. So we're going to use the topology, and we're going to use the pointwise addition that the vector space characterization gives us. We also get scalar multiplication if we want it. So that means if we have some object in our space of arithmetic functions, we can multiply it by some number to scale up each of the entries, some complex number. So in the same way that these are a vector space, we have all of these different projections. So for each of the indices, for each of the natural number indexes, we can take an object in our space. So f would be an object inside of our arithmetic function space. And for each of these indexes k, we can take its projection down. So this p sub k would be the kth projection. And when we apply that function to f, which would be one of our functions, or one of our objects, our vectors in our arithmetic function space, would get us the kth component of that function. So this mapping, of course, it's linear because it's a projection. It's continuous also because it's a projection. So it's linear and continuous. Instead of treating our objects like functions, we're going to always use this projection notation. So if you ever need to fall back on the function notation, you can. But usually we're just going to think of these as projections. So we have vectors, and we have our vectors like f inside of our space A, and we can project them down. So for each index k in the natural numbers, we can project it down. And if we know what all of the projections are, then we know what the function is. Or we know what the vector is. All right, so there's some other notes here about the topology that we're going to end up using. So the first observation actually that we make is fairly complicated. Our first observation is that the space is locally convex. Give me just a second. Our first observation is that the space is locally convex. And what that means is that so we have because we have our space as being a vector space over the complex numbers, it's also a vector space over the real numbers. And so you might know, and actually I can pull up another little thing here that we can type on. So a set is convex when we have for each of, let's say, xt plus y 1 minus t. Okay, so the characterization of a, there we go. The characterization of a convex set, so like here we have a set, some set S, which we presume is in a vector space. And if we have two sort of points in this set, x and y, and we also have a number t, which is in 0 to 1, we can take this convex sum, so x times t plus y times 1 minus t. And whenever we take a convex sum like this, that will also be in the set S. So that's what it means for a set to be convex. It's convex if all of these convex sums are in the set. And so what you can think about this basically is that this little linear function, this is just the line segment that starts at x and then ends at y. So another way to think about these convex sets is that they contain all the line segments in them. That all of the line segments from point A to point B inside the set stays in the set. So that's a convex set in the general case. So over here, our first observation is that our space is locally convex. So what that means is that if we have an open set in our topology out of our space A, if we have an open set and we have a point in that open set, then we can actually find a neighborhood that's smaller than the first open set of that point, which is a convex neighborhood. So every point has a basis of convex neighborhoods, which a basis means all of the open sets can be generated just using convex sets. So this is really useful if we ever need to use convexity. Then we'll be able to use this locally convex property, and sometimes we will mean locally convex. We also have Hausdorff. That's a really simple condition that you probably maybe remember from topology. Basically just means that two different points can be separated topologically. So if you have point A and point B, that they have disjoint neighborhoods. So you can sort of put stuff between them to make them be farther apart. Second countable and metrizable, both of these properties, essentially they're just saying that our space is very similar to a real Euclidean space. So the real Euclidean spaces like R1, R2, R3, they have really nice properties. Our space is sort of because we have infinitely many dimensions, it's sort of the least complex thing that's more complicated than all the Euclidean spaces. But fortunately, it has these nice topological properties. One of those properties is that it's a sequential space. Not all topologies are sequential spaces. What it means to be a sequential space is that you can essentially define the topology in terms of sequences. So if you want to know if a function is continuous, it's enough to just consider a sequence of inputs tending to a point, and you can just figure out if that sequence has a limit when you apply the function. And so that sort of characterization is really useful for because it means we only have to think about sort of simple sequences which are countable, sort of objects. So we don't have to worry too much about higher topological notions of continuity. We can just think about sequences just like you would in real numbers. Okay, so those are sort of the key notions. We also have one other useful thing, which is that the sequential because we're in actually not just because we're in a compact space, but because we have a very nice topology, the notions of compactness and sequential compactness happen to be the same. And so what that means is compactness is a very sort of nebulous concept in topology. Sequential compactness basically just means that every sequence, every bounded sequence has a convergent subsequence. Or rather, every sequence has a convergent subsequence. And it just so happens that in this topology, compactness, which is this really complicated concept, and sequential compactness are the same. That's also true for real numbers and all other Euclidean spaces. Not all spaces have that property, but this space does have that property. So our arithmetic function space, sequential compactness and compactness are the same thing, so we don't have to worry too much about that. So these are sort of the topological preliminaries. And so next, just getting right into the definitions of the actual functions that we'll be using, are the sort of key operation here that we'll be talking about the whole time is this operation of Dirichlet product. So Dirichlet product, it's a binary operation between two elements of our space, of our arithmetic function space. And the way that we define it is that we run across ordered divisor pairs and we multiply them together. So, for example, when we product two of our elements in our space together, we get another element in our space, which is going to be another sort of complex sequence. In order to figure out its behavior, we have to ask what is its value on each of the projections. So in order to know what is the value of one of these sequences, we have to figure out what its value on each projection is, and so that we know what the object is. And so the definition is that each projection, so if you have some index k, which is going to be, again, it's a natural number, we have some index k, and if we take x and y, we multiply them together, and when we project them down onto the kth axis, the value will be this sum. So it's a sum across d, which is a divisor of, I don't know if you can see that, let me scroll down. Yeah, so it's a sum across d, which is a divisor of k. So we're going through all the divisors of k. So for example, if k was 6, then we go through 1, 2, 3, and then 6. Those are the divisors of 6. So we'd sum across all the values of d, which are a divisor of k. And the term that we're adding together is we take x and project it onto the dth axis. So we take its d component. And then for y, we would take the k divided by d. So because d is a divisor of k divided by d is also a divisor of k. So that's why it's a divisor, sort of divisor pairs. And we project y onto the sort of corresponding divisor pair axis. And we multiply those values together, and we sum them all up. There are some other equivalent characterizations we might use. So this second characterization is really the same thing, but we might use this notation sometimes. We'll sum across values a and b, so these will be integers. So we'll sum across integers a and b, and whenever these, for each ordered pair, a and b, which multiply to be k, we'll take the projection of x onto the ath dimension and the projection of y onto the bth dimension. We'll multiply those together, and then for each of those ordered divisor pairs, we'll sum them all up. This last characterization is sort of the same as this second one, but we just sort of made the indexing a little more explicit. So we're running over ordered pairs a and b in natural numbers with the condition that their product is k. So that's sort of the definition of the Dirichlet product, and we're going to find out that it has lots of useful, interesting properties. One of the interesting properties, so for each, because we're sort of in like a vector space, we want to be able to talk about the basis vectors sometimes, sort of the standard basis units. So for each index n as a natural number, we'll let e sub n be an object in A, so we'll have sort of a sequence of these e sub n's. And this will stand for it'll be the nth standard basis vector. So the projection onto the kth axis of e sub n is 1 if n equals k, otherwise it's 0. So it's sort of the indicator for just the nth dimension. So it'll be 1 on the nth dimension and 0 everywhere else. So in that sense, we can sort of think about it as a sort of standard unit vector. The property that these have, so we know that because we're in a vector space, and especially using our limits, any element of our space can be represented as a sum of across these standard basis vectors. So we can take these basis vectors, multiply them by a coefficient, and then we can add them all together, and that would give us a unique representation. Of course, because we have infinitely many of them, we have to add them together in limit, but it's still valid, it still works out. So it's not quite a basis, but it's functionally sort of the same. So an interesting characterization of these basis vectors, and of the Dirichlet product in general, is that if you take any two of these basis vectors and you use this product, if you multiply them together with the Dirichlet product, it's the same as just multiplying their indices. So the second, for example, the second basis vector multiplied by the third basis vector would give you the sixth basis vector. And that's sort of a really simple characterization. It's basically just integer multiplication, but we're using basis vectors instead of integers and different dimensions. But the characterization itself is rather straightforward. Okay, so we have this characterization of these objects, and one of the key properties is that if we pair our set of arithmetic functions, our A space, with pointwise addition and with the Dirichlet product, that forms a commutative ring. And so what that means is we have addition is, so of course addition forms an abelian group. That means addition is commutative and associative. Also, Dirichlet product is also commutative and associative. So if we, like up here we were talking about what happens, when we convolute x with y, well, we can also reverse the direction. X times y is the same as y times x. Even though our product has this really weird, complicated definition, it just turns out that it doesn't matter what order you multiply things in. It also doesn't matter what order you associate them in. And also, more importantly, because it's a ring, convolution will distribute over pointwise addition. So it'll distribute over plus. So we have all these really nice properties of arithmetic. Of course, the 0 element is the 0 vector. That's straightforward, as because we already know that we're sort of working off the vector space idea. So 0 is our additive identity. the multiplicative identity is actually the first basis vector. So that if you take the first basis vector and you convolute it with any object in the space, you just get whatever the second thing was that you picked. So that second thing just always sort of comes out. So that's our unit, and we have our 0, and we have a ring. So we have all these really nice properties. Another thing that's really nice, and this is really important, which is that our Dirichlet product is continuous in our topology. So the way that we know that something is continuous is a function is continuous in our space if and only if it is continuous on each projection. So up here we have our definition in terms of the projections. So whenever we multiply two objects together, we can project them down to figure out what the result is. And on each of these projections, we just get a finite sum of a finite product of other projections. We know that the projection is always continuous, and of course sum is continuous, and on the complex numbers, product is also continuous. So each of these projections are continuous in both x and y, and that means that the product is continuous in general. So if it's continuous on each projection, then it's continuous in general, and that's what we've got here. That actually, in addition to the fact that we have, it's a vector space, it's a topological space, it's also a topological ring, so all of our operations are continuous. So instead of treating them more like vectors, we're going to try to treat them more like numbers. So instead of thinking of them as, vectors with different, different projections, we'll still use the projection functions. But we actually want to think of them more similar to multidimensional numbers, sort of like how complex numbers have a real part and imaginary part. It's just here we have infinitely many parts to our multidimensional numbers. And so we're going to try to be thinking about them in terms of that. What we're going to do in pursuit of treating them more like regular numbers is we're going to find a way to sort of fit the complex numbers underneath them, structurally speaking. So we're going to look at this this subset of our space that we're thinking about. So we're labeling this subset. So we've got the blackboard C and then subscript A. This is just a temporary label, but C sub A is the set of all these elements Z in our space. So all of our little vectors or arithmetic function objects, and we're going to take each one of these objects which satisfy the proposition that all of the indices n greater than 1, so all of the indices after the first one, have this projection being 0. That's a typo. Let me fix that. So all of our so we want all of our projections after the first one. When we project them down, we want them to all to be 0. So another way of thinking about that characterization, I'm recompiling here. There we go. Another way to think about this characterization is we want essentially only the first index is going to be non-zero. So we'll have something on the first index as being non-zero, and then the rest of them will just be all zeros. Another way to think about that is if we just take our E1, our first basis vector, we can just multiply it by a complex number, Z. So we take E1 and multiply it by some complex number. So that just scales that first index up by Z in the complex direction Z. So of course, given this sort of second characterization, this function, which maps a complex number Z over to Z times E1, the first basis vector, that's a bijection. We know that's a bijection because E1 is not 0, so this product will be 0 only if Z is 0. And if Z is not 0, you can just go in reverse by dividing off Z, or taking the first projection. So this is this function is actually a bijection. So it's a bijection between the complex numbers and this special subset that we just specified, which is the set where they're only non-zero on the first index. This function has the inverse function as the first projection. So the first projection is the inverse function of this sort of inclusion map here. The first projection is the inverse function, And the first projection is linear. So our inclusion map from the complex numbers into our new space of numbers is a linear function. We can also verify actually really easily that in general, if we take some complex number s and we send it through this inclusion map to turn it into an element of our space, if we multiply this with the Dirichlet product, if we multiply this by any object x that's in our space, it's the same as just pointwise multiplying s in the first place. So whether or not we include x into our new space and then use the Dirichlet product, or if we just use the vector space pointwise multiplication, it's actually the same thing. And that's really useful because if, for example, instead of just doing x, if we had two complex numbers and we include both of them into the space, and then we use the Dirichlet product on them, it's the same as just using this pointwise multiplication of s on the second one. But this inclusion map is linear, so we can just pull the s in. And this ends up being the inclusion of s times z. So if we have this inclusion map, so you might notice this is the isomorphism property. If we multiply two functions when we put them through this inclusion map first, and then multiply them, it's the same as if we multiply them in the complex plane, and then we take the result and map that back out into our wider space of numbers. And so because this so it's a linear function, it's a bijection, and it has this isomorphism property for multiplication, that makes it an isomorphism between rings. So in fact, this inclusion map, z mapping to z times e1, this inclusion mapping from the complex numbers over to this set here that we've defined, is an isomorphism. So these two rings are the same isomorphically. They're also a homeomorphism. Both of these mappings, the first projection is continuous, and this mapping from z to z times e1, this scalar multiplication, is also continuous. So not only is it an isomorphism of rings, it's also a homeomorphism. So it's an isomorphism of topologies. And so what that means is that basically in essentially every way that we care about, these two objects are just exactly identical. And so because they're identical in every way that we care about, we can just treat them as that they're actually the same thing. So we're going to sort of turn this little inclusion operator, we're going to make it implicit. So we're going to just treat it as if it's always there. Whenever we need to use it, we'll just pretend that it's already there. So we'll treat the complex numbers as being equivalent to this set, which is a subset of our arithmetic function space. So what we're doing essentially is we're saying, if we have a complex number, z, in the complex number space, we can include this implicitly as one of our arithmetic functions where we just turn the first index to whatever that complex number is, and then we ignore all the rest of them. So we're just going to treat the rest of the indices as 0. So the complex number space is the subspace of our arithmetic function space, where only the first index is non-zero. They're equivalent by our isomorphism. So for example, this means our first basis vector, e1, is actually just 1. We can just write 1 for that if we want. It's actually just the unit. So e1 is 1. The first basis vector, the first direction, is the unity. And it also has the fact that, of course, we can see that really clear right here, in fact, and also here, that scalar multiplication, Dirichlet product, and complex multiplication are all the exact same thing under this isomorphism. They're all exactly identical operations, which is super useful because it means even though we have these three different, structures that we're thinking about, we have vector space and we have complex numbers and we have Dirichlet product. In this context, they just all end up being exactly the same thing. So if we look at it through this isomorphism, they're just the same. And that's what we'll be doing. So that's sort of the first critical part. So that's sort of the initial setup. From there, our next most important property is that in addition to the fact that so we have our ring here, our A set with plus and Dirichlet product, not only is it a commutative ring, but it's also an integral domain. And so what that means is that it has the zero product property. So If you multiply two numbers together and you get the 0, then one of the two numbers you multiplied has to be 0. That's sort of the integral domain property. So the way to prove that is we're going to define a special function in order to prove that, and we're not going to prove it explicitly, although if you want, we can. But we'll define this special function z, and for each of the inputs x, so x will be an object in our space of higher numbers. For each element x, we'll take the infimum of all the indices k, where the kth projection is non-zero. So a way to think about this is that so we know that each of our numbers in our space is sort of like a complex sequence. It's possible for some of those elements to just be 0. So for example, the E2 basis vector is 0 on the first index, and then it's 1 on the second index, because that's sort of the property of being the second basis vector, and then the rest of them are 0. And what we want to know, what the z function is asking, is how many zeros are to the left, sort of. How many low index zeros are there? So in the case of E2, the z function would output 2. So it's the infimum of the k indices where the projection is non-zero. Well, for the E2 basis vector, the second basis vector, the only index where it's non-zero is the second one. And the first one has this first projection of E2 would be 0. So z of E2 would be 2. Likewise, z of E3 would be 3, and z of E4 would be E4. So we're sort of wanting to know how many zeros does our sequence start with. In the case, so we actually have this function defined between not just integers, but extended integers. We have a little overline here. So in the case that all of them are 0, if all of the indices are 0, then we have the 0 vector, and we're just going to say that's infinity. So in the case that all of the the entries are 0, then we'll give it the label of infinity. And the reason we're doing that is because, well, not only does it just sort of naturally fall out of this infimum calculation, but we sort of want to know how close or far away is our input from 0 itself. It's sort of in a reciprocal sense. So the higher the z value is, the closer it is to 0, the more 0 entries it has. And the useful property of this function, the reason that we want to talk about it, is that it's actually multiplicative. So if we have, if we multiply two elements together and then we apply the z function, it's the same as applying the z function to each one independently and multiplying those. And that also works in the case of where one of them is 0 or infinite. That also works in the case where one of them is 0 is infinite, where infinity times any positive extended integer is just going to give us infinity again. So infinity times 1 or 2 or 3 will just be infinite. The fact that this function is multiplicative is, you can sort of see it actually from this earlier property we had. So earlier we said each of our basis vectors, our e sub n, have this property that if we multiply e sub n with e sub m, then the result is that we multiply the index together. And so this is sort of foreshadowing. So of course we can see it really clearly. The z function, if we apply z to this e sub n, we know it's 0, 0, 0, 0, 0 until we get to the nth index, and then it's 1. And likewise for this m. And when we multiply them together, we get this e sub n m, where we multiply their index, the dimension together. And that gives us as many zeros as that. So this is sort of the foreshadowing of that. And actually you can use this fact, if you just use this fact on its own, you can actually use this to figure out really quickly that when you multiply two things together, that the z function is multiplicative. Because the z function is sort of saying, only the lowest non-zero index matters. That's sort of one way you can think about it. So this z function is, where were we? Here we are. So the z function is multiplicative. And that's really useful because that actually tells us that we're working in an integral domain, that we have the zero product property. because of course, if we have, x is non-zero and y is non-zero, and we multiply them together, well, the z value of their product will be the product of their z values. And if both of them are non-zero, then both of their z values will be finite, will be not infinite, which means that the z value of their product will also be finite, which means that their product can't be zero. This z function is useful for lots of other reasons. So eventually what we want to do is we want to start using sort of analytical properties. So we're going to get into how can we use Dirichlet product in how can we use the Dirichlet product in power series? So if we want to think about things like that, then we'll have to have different ways of sort of measuring the convergence properties, which normally we don't really have. So the z function is one of the tools we'll use to sort of measure, how quickly does something converge, or can I get something to converge really fast, which will be useful for estimations. This also lets us use, so if we have the zero product property, this is actually equivalent to the cancellation property for multiplication. So if we're, because we have, for here. So because we have the zero product property, if we have, x, y, and z, which are elements in our space, if x is non-zero, and we have x times y is equal to x times z, then actually we end up with y equals z. And the reason that happens is actually it's an immediate consequence of the zero product property. What you can do to prove this is if you have x times y equals x times z, you can subtract x times z, then you can factor out x, and you'll get x times y minus z as equaling 0. But we have the zero product property, and we specified that x wasn't 0, so it has to be that y minus z is actually the thing which is 0. And of course that just immediately gives us that y equals z. So the zero product property and the cancellation property are actually the same thing, as it happens. So we do, because we're in an integral domain, because we have the zero product property, we have cancellation. And that's super useful as well. Whenever you have cancellation, you can define division. So if we have some elements x and y in our space A, we'll define this relation here. So this is the proportional to symbol. So we'll define this relation: x is proportional to y is true when both y is non-zero and also there is there is some element z such that x equals y times z. So if x is equal to y times z, given that y is non-zero, which was our first condition on this proportionality to be true, given that y is non-zero, then we can sort of cancel off this y, this z that satisfies x equals y times z is actually unique. There's no other z that could satisfy this relation between x and y. So this value of z is unique, and that lets us define a function. So if we have x and y, and x is proportional to y, which means y is non-zero, and there is some z so that x is y times z, then we're going to define the fraction x divided by y is defined as equaling z. So whatever z happens to be, we'll just have x divided by y as equaling that result, that unique value. So of course this has sort of all of the properties you want out of a fraction. If you have x divided by y and you multiply by y, then of course you'll get x again, because x equals y times z. We also have all sorts of addition properties. You can add fractions in the way that you would expect. You can combine fractions, and so on. We'll get to those more later, but you can sort of work through all these properties to figure out that they work out. So that's our division so far. So as a quick recap, we have defined our set as the set of arithmetic functions, that's complex number sequences. We've given them a topology, we've given them pointwise addition, we've given them all these projections that let us sort of talk about their different properties. We've defined this Dirichlet product, which is sort of a really important object for our study. we've found that it's continuous and has all these nice properties. So it forms a commutative ring and an integral domain. And we have defined, we've also given them, this is our sort of critical isomorphism, we've interpreted this this set as an extension of the complex numbers. So our complex numbers are sort of the two-dimensional, you know, small subring of our higher space A. And we've also discovered this cancellation and this division. So these are sort of the things we've gone over so far. Do you have any questions? Well, okay, so you can ask whenever you, if you think of anything, you can ask a question. Nice, that is so great. That's what I love to hear, is that you're understanding. That's my favorite thing. Okay, so we've got our ring, and we're using it as an extension of the complex numbers. We have some division here, so we're going to continue on. So the next thing we want to talk about is, so we don't have a field. So a field would be if our division is always defined. Nice. So a field is if division is always defined whenever y is non-zero. We do have that y is required to be non-zero. So another way to think of this proportionality thing, if we're saying x is proportional to y, actually what we're saying is that x is able to be divided by y. And this statement is not always true. Sometimes, even though y is non-zero, it might be the case that z doesn't exist. There's no z to satisfy this relation. If there was always such a z whenever y is non-zero, then we would be in a field. So we could always divide by something non-zero. But we're not in a field, which is why we have to have this proportionality relation. But we can talk about sometimes, for some values of y, this value of z will always exist. So the values in an integral domain, which you can always divide by, are called units. So if you can divide by something always, it's called a unit. And we're going to have our set of units, we're going to call it a sub star. So usually you'll probably see like r star or c star as being the set of non-zero real numbers or the set of non-zero complex numbers, respectively. Instead of interpreting that as the set of non-zero elements, we're actually going to interpret it as the set of units. So it's the set of things which you can divide by. Of course, for complex numbers and real numbers, only 0 is the only exception. But here we have some more exceptions. But we have a really nice characterization for the exceptions. So our A star, our set of units, is the set of all x in our A space, such that 1 is proportional to x. So it's the set of all x such that 1 can be divided by x. And that sort of like makes sense, right? You can also think of this, this proportionality, x is proportional to y. If 1 is proportional to x, then there's some z such that 1 equals x times z. So z would be the inverse of x. So if 1 can be divided by x, then x is a unit. The equivalent characterization we have for this is that x is a unit exactly when its z value is 1. So that means its first index projection is non-zero. If its first index projection is non-zero, so that's this characterization here, for a P1, the first projection is non-zero, the first component or the first part. So if the first part is non-zero, then our value is a unit, if we can divide by it, no matter what. If it's 0, then it's not a unit, and we can only sometimes divide by it. Of course, another way to interpret this, because this is the set of values where the first projection is non-zero, we can also think of this as the pre-projection, so the pre-image of the first projection of C star, the set of non-zero complex numbers. It's all of the numbers which, when you put them through the first projection, gives you a non-zero number. So it's the pre-projection of C star. So A star is the pre-projection of C star, which is very nice. So we don't have a proof for that. We actually are going to have a proof for this in a minute. But this is sort of a well-known property. We can go over it a little bit later if you like. But this is sort of neat. We actually find out in our study, so this is a well-known property, but in our study, as I continue to add on to this draft, we're actually going to see that the first pre-projection is actually really important for these higher functions that we're going to be studying. So we're going to see this again. So it's not only the reciprocal function, hint hint, it's not only the reciprocal function which has this first pre-projection as deciding its domain. There are other functions where this first pre-projection will decide the domain. But we'll eventually get to that someday. So whenever we have some x as a unit, we can write x, power -1, or we can write 1 divided by x interchangeably. So because we sort of defined this fraction notation, we can just sort of use these however we want, one or the other, depending on whichever one's more convenient at the time. More generally, in terms of these exponents, if we have any element of our space, we'll define an integer exponentation. So x to the power of 0 is 1, which is also our E1 basis vector, so it's the unit. And inductively, if we want to raise x to the nth power, we just take the previous power and just multiply it one more time by x. So that's sort of standard. So this integer exponentation is just repeated Dirichlet product. So however many times we want to multiply x by itself, we'll just use a superscript n, which is pretty normal. And then if x is a unit, if it's an A star, then likewise we can also use negative integers. And this has sort of the same, this always happens in a ring. Whenever you can take inverses like this, if you have x to the power of n and then you take the inverse, or if you take the inverse first and then raise it to the power of n, they're both actually the same thing. And of course you can also think of that as x to the power of 1 minus n and then divided by x. All of these are equivalent. So integer exponentation, sort of standard, except we're just using Dirichlet product to define it. These will be used a lot. We are eventually going to get into power series for Dirichlet product power series, so power series in this A space, and we'll be using these integer exponents a lot. Okay, so we're going to define, so we have more analytical tools. So we're going to define this subset. I've just sort of labeled it A sub r. This is sort of the fancy script real part operator down here. This is the set of all of our elements in our space where all of the projections are real numbers. So our general space is all complex sequences or all complex vectors. And this A sub r is the subspace where we actually only want the ones which are real. So real on every index, or real on every projection. Equivalently, this is our power n, and it's a sort of a subset of our total space. This subset is it's a subspace. It's a vector subspace. It's also a closed set topologically. So of course, because our limits are pointwise, if we take a limit of some vectors which have all real entries, the result will also be, some vector with real entries. So it's topologically closed, and it's also a subring, so that just means it's closed under addition, and it's closed under multiplication. That closed under multiplication part is also sort of straightforward. We can go back up to our definition for Dirichlet product. So up here, if x and y have all real entries, when we multiply them together and then we project them onto the kth, projection, well, that calculation is just, take the various projections of x and take the various projections of y, multiply them together and add them all up. And of course, if all the projections are real, then the products will be real and the sum will be real. So if we take x and y and we start to use our Dirichlet product to put them together, if x and y were real, then the result is also real. And that's pretty straightforward. So this A sub r, it's a topologically closed subring, which is what we just went over. So we can also turn this, so unlike our general space, we can actually turn this into an ordered vector space over the real numbers. Similar to how, so there's no less than or greater than relationship on the complex numbers, and that's because, you know, they're two-dimensional, so they're not linearly ordered, and so that sort of applies here as well. We still can't have a proper total order that like makes a good sense, but we can still find a partial order which will help us a lot. So what we're going to do is we're going to define a partial order relation. So it's this little precession relation. So we'll say x is preceding or equal to y. This relation is equivalent to the statement that on every index, so on every k in our natural numbers, the projection of x is less than or equal to the projection of y. So we can sort of think about that like cones almost. It's sort of hard to visualize. I think I want to say, if you've ever done real analysis, this is similar to the idea of absolute continuity, where sort of on every sort of index, on every projection, this x is less than or equal to the same projection of y. So it's sort of dominated by y on every projection. This isn't a total order. It's possible for some projections to be larger and some projections to be less. So not every two elements can be compared. But among the ones that can be compared, this relation is reflexive, transitive, antisymmetric, and compatible with addition. So what does that mean? So reflexive means that each object relates to itself. So this sort of precession operator, it's a weak partial order, which means that x is preceding or equal to x. In particular, x is equal to x. So of course this relationship would be satisfied. As for the other ones, so transitive means that if x precedes y and y precedes z, then x also precedes z. So this is very useful. It's antisymmetric, so what that means is that if x precedes y and y also precedes x, then x and y are equal. That's this one right here. So antisymmetric means we don't have any sort of symmetrical pairs. If you can swap them, then actually they're the same thing. And the last one is that it's compatible with addition. So if x precedes y, then x plus z, where z is just anything we want, any real vector that we want, then will also precede y plus z. So all of these properties are really familiar to us for real numbers and the standard, you know, less than or equal to total order. The only difference, actually, between this relation and the behavior of the total order on the real numbers is that not every pair of elements are comparable. Among the ones that are comparable, though, we have all of these relationships, which are very nice. In conjunction with this, so we're not going to frequently run into objects that are in this real subring. We're not going to frequently run into those. In fact, most of the things we'll be studying will be assumed complex unless stated otherwise. But we want to be able to use this relation because it has these nice comparative properties where we can sort of put something underneath something else and make some approximations like that. So in order to use this more frequently, we're going to define a function which takes any element of our general complex space and it's going to map it down into the space where all the entries are real, this real arithmetic functions. And the definition of this, it's really similar to absolute value. It's not quite the same, but it's similar. The definition is that for each x in our space, and for every index. So we want to figure out what's the value of these evaluations on each projection. So for every projection, for every kth projection, our A, our absolute value of x, is defined as equaling just the absolute value of the projection. So whenever we apply this A function on x, actually what we're saying is take each index, you take each part in each direction, and take its absolute value. And that's actually, as it turns out, is super useful for a whole lot of things. So whenever we have some presumed complex sequence, we can apply this A function, and we'll get some real sequence where it's just the absolute value on each index. Because this is defined in terms of the actual absolute value bars for the complex number space, it inherits all of the usual properties, almost all of them, except instead of less than or equal to, we'll have to use this precession, precedes or is equal to. So it'll inherit, so it'll be non-negative, of course, because it's we're taking the absolute value on each index, on each projection. It'll always be a positive on each index. So not only will it be real, but it'll be positive. And so that's this first one. It's also going to be positive definite. So what that means is that if we do, so this here doesn't restrict that the element is not 0. It might be 0, but if it's 0, then the input is also 0. So that's what positive definite means, is that if our input gives us something that is 0, then the input also has to be 0. So if the output is 0, the input is 0. We also have the triangle inequality, and that's this one right here. So this basically falls out immediately out of the triangle inequality for complex numbers as a complex norm, which is that because we're just taking the absolute value on each index, and because this precession relation is on, it's pointwise, it's on each index, then we get the triangle inequality here as well. So if we apply this absolute terms of x and y, then that will precede the absolute value on x plus the absolute value on y. I'm actually not really sure how to say this out loud. It's just kind of a symbol in my brain. It's not really an absolute value, actually, which is, as it turns out, not as important as one would think it would be. It would be an absolute value if it were multiplicative, but it is not multiplicative. It's actually sub-multiplicative. And that means that if we have x and y and we multiply them together, instead of being equal to the product of these, of the absolute value of x and y, it's preceding or equal to. So it won't always be equal to. In fact, usually it will not be equal to. Usually. But as it turns out, this is just as good. Usually we want to use, in complex analysis or in real analysis, you want to use absolute value bars to sort of approximate things. How can we put an upper bound or a lower bound on the growth of something? And this inequality works just as well for almost every use case. And for the use cases where it doesn't apply, usually it doesn't matter because the thing you want to prove is false. So it just ends up working out really nicely. So we don't have multiplicativity, but we do have this sub-multiplicative property. And if you want, actually, we can write up a proof of this real quick. So I don't have a proof here. And of course, I just made this function up, so this isn't really well known. So you can just write a proof. Give me just a sec. So our claim is, actually I'll scroll down. Down to around here. Oh, whoops. Right. Okay, where are we? Right here. Okay, so we're going to write a theorem real quick. And I'm going to prove this. So we have a of x times y preceding or equal to a of x and then a of y. There's our theorem statement. Okay, so, and we're going to prove this real quick. So actually I can, let me share a bit more of my screen so you can see what I'm typing. I will do, I think I can just do this. There we go, now I can see a little more. I hope that's not too weird looking. Yeah, that looks fine. Okay, so I'm over here typing on the left side, so I've got overleaf here, is what I'm typing on. On the left side, I've got the LaTeX code. On the right side, we've got our theorem that we're going to be proving. So I'm going to start a proof here. So what do we want to do? So in order to work this out, we should try to work out this x times y first. So in order to prove this precession relation, we want to prove a less than or equal to, yeah, simplified. Hey, you know, it's a lot better, actually, not to get too far on a tangent, but my preliminaries only took 2 pages in this version, and in the first version, it took 20 pages, so it's definitely, you know, we're going along here, so, okay, so, so we want to prove this theorem. So in order to prove this precession relation, we want to prove a less than or equal to relation on each index. So I'll start by writing that down. So projection k, and we'll do a of x times y, definitely densified, as less than or equal to pk of a x times a y. So I'm sure this is going to be a little fuzzy for you since I'm a lot more zoomed out than I was before. So our first, oh, I don't like that. That's better. Okay, so for each of our indexes, k, we want to show that the pk projection, so the kth projection, the projection onto the k direction of this, you know, a of x times y is less than or equal to this projection. So that's what this precession means. If we're saying this precedes that, then we want to say each of the projections is less than or equal to each of the other ones, correspondingly. So we want to prove this relationship. And so in order to do that, of course we know, so we want, and actually we're, this is going to be, again, I'll show you sort of my proof technique, how I prove things. So we'll go in reverse for what we need to do. So I know in advance that this will work out and be true, and the proof is not too long. So we'll go in reverse. So we want to show that each of these things is less than or equal to. So we'll sort of go in reverse. So how do we prove this statement? Well, we know that, you know, on each index, when we project down the a of some term, we actually just get the absolute value of the projection. So on the next line down, instead of doing the a on the inside, we can do an absolute value. So that's sort of our first step. That's on the left side. On the right side, we want to expand out this product here. So to do that, we'll do a sum, and we know that we'll do sum across ordered divisor pairs, ab equals k. We'll have the first term projected onto a, and then we'll have the second term projected onto b. So it'll end up like that. There we go. So we're going sort of in reverse now. So these don't follow logically yet. So we want to show that this is, that this absolute value term here is less than or equal to that absolute value term. Actually, I don't need the projection anymore, sorry. That is the projection. There we go, yeah. So we want to show that this summation is less than or equal to that. But again, here on the right side, so actually we can do the same thing on the left side. So we have this pk on the left side. So we can similarly do ab equals k. We'll do pa of x and then pb of y. So here we're just expanding out the definitions of convolution. Right, so we want to show that this thing over here is less than or equal to this thing over here. If we go a little farther than this, so we know on the right side, we have this projection of this a function, twice in fact, and we know that by definition this a function is the absolute value on each index. So if we project onto b of a of y, that's the same as the absolute value of the projection of y. So we'll just do that out real quick. So on the next line down, instead of writing a, we'll have absolute value bars on the projection. So we end up with this. And this, you might notice, this is actually just sort of the triangle inequality, but more, is that we have this sum, because we can actually, on this right side, if we'd like, we can, instead of having a product of absolute values, we can have an absolute value of products. And that just is true. That's the triangle inequality. The absolute value of this projection, of this summation, is less than or equal to the summation of the absolute values. That's just triangle inequality. So we have a statement that's clearly true, and we can, in order to get up to these other statements that we want to prove, we just go in reverse. So we just follow all the steps that we just did, but in reverse order. So what I'm going to do is I'm going to copy this little thing that I just made, and I'm just going to put each of the lines in reverse order. So this is sort of a, that one is the first one, this one is the second one, and then this one will be the third one, and the last one is what's left. And hopefully I did that in the right order. Whoops. Align environment doesn't like white space. And I'm going to get rid of this other one because that's cluttering it up. Okay, so what we have is we have this this sort of sum of these projections. So we have this summation across these indices. So whatever the sum is, we just sort of pull it out of thin air. This summation, if we take the absolute value of this because of the triangle inequality, this is less than or equal to the sum of the absolute values. But of course, the sum of the absolute values, this is just the, if we have the absolute value of the product, it's the same as the product of absolute values. And on this right side, the absolute value of the projection is just the projection of this a function. So we've worked down, so we have this sort of self-evident triangle inequality, and we've worked down the right side. We can work down to here, and we can work down to here, and we can go one further step, which is that this summation of this projection of this thing times this projection of that thing, this is just the convolution of the kth projection. So this whole right side, and actually let me actually use the align environment like it was intended to be used. Oops. There we go, and actually align everything. So all of these right sides are equal. The left sides are also equal. Actually, we don't even change the left side at all until the very end, which is that this is just the absolute value of the projection. We can also do, we can update this left side a little bit more to make it more clear. So this absolute value of the sum, well, this sum is just p sub k of x times y. And then in the next line, the absolute value of p sub k, that is just the a of the absolute value. So a of the projection. or sorry, P of A. Oops. Okay, let's try that. And so that's the proof. Because we have this triangle inequality follows for each index, and then we just, each of these sides just sort of works down, and we get this term here. And because this works for every k, then of course this will work in general. So we get our desired result. So instead of doing the projections, because this works for all of them, we can just do the terms themselves. And actually this proof is so self-evident that we don't need very much commentary. So that's the proof. So in order to prove this precession inequality, it's just the triangle inequality on each index. So this inequality, for as simple as it is, it's very useful for us because it lets us make all sorts of approximations. So we're just going to leave this here in the appendix and return back to where we were, which was right here. So we're studying the properties of this a function. So that is how we use the a function. That's how we write up a proof for that. So moving on from that, our next sort of observation. So we have a characterization. I sort of briefly mentioned this way back in the beginning. The notions of compactness and sequential compactness are the same thing in this topology. And actually we have a really simple characterization of these sets, which is that the compact sets are exactly the closed sets where every projection is a bounded set. So if we take a closed set and we do each projection, and if its image on each projection is bounded and it's a closed set, then it's a compact set. And that may sound really familiar, because if we phrase it in terms of this a function, we actually have equivalently a set is compact if and only if it's closed and bounded. If we were using, so just to be clear, and we're about to get into this in a minute, we are in a metrizable space, which means we have there is a distance function which generates the topology. If we used the distance function to define compact sets, it would be very not useful. You in fact wouldn't get this property that a compact set is closed if and only if is compact if and only it's closed and bounded. You actually wouldn't get that if your definition of bounded was in terms of the metric. In fact, every open set is unbounded. So not in terms of the metric, but on some projection. And that's because we have infinitely many dimensions, actually, specifically because of that. But in terms of the a function, it is compact if and only if it's closed and bounded, where by bounded, what we mean is there's some bound b, which is a sequence value, it's a real sequence, and it bounds the image. So if we take the image of our compact set and we send it through the a function, so we take the absolute value on each index, this will be a positive. So every element in K, when we apply the a function, will be preceding or equal, succeeding or equal to 0. That's sort of our non-negativity property of our a function. If we can bound it by some constant b, so if there's some b where every single object in this projection is bounded by b, then the set is bounded. It's bounded on every index. And if we can make this be true, if our k set is bounded by b when you apply the a function, and also it's a closed set, then it's compact. And if it's not bounded by b, or if it's not closed, then it won't be compact. It won't be sequentially compact. So that's a really nice characterization of compact sets, and we will use that because compact sets have a lot of usefulness for continuity, proving continuity and different sorts of convergence. So we'll be using that several times. Our a function can also be used to define uniform convergence and Cauchy sequences. So normally these would be defined in terms of a distance function, but we're actually going to be defining them in terms of our a function. And the reason we're doing that is that our distance function doesn't really play very well with our Dirichlet product. There's no real expectation that this weird distance, so this is actually a distance function that we might use if we were going to use one. There's no real indication that this would play nice with the Dirichlet product. We don't have any expectation that it would like the Dirichlet product, that they would give us some useful approximations. But we do know that our a function does do that. So our a function plays very nice with the Dirichlet product. We have this submultiplicativity, better than multiplicativity even. So anyway, so we can define uniform convergent Cauchy sequences. So the way we're going to do that is, so we're going to reference this this metric here. So we're not going to prove that this is a metric for a topology. This is just sort of one of the nuances of the topology we're using, is that this function is a metric function, which generates our topology, which would make our space a complete metric space, not just a metric space, but a complete metric space. Instead of using this metric though, so normally when you're talking about uniform convergence and Cauchy sequences, actually they're very related concepts. Is you want to take some set of things and you want to figure out sort of what's the largest distance between any two things in this set. So for Cauchy sequences, your set of things are sort of all the tail elements of your sequence, and you want to figure out what's the largest distance between, you know, two elements in your sequence that occur some point after you know, some initial index, some lower bound. And so that's sort of how you would define a Cauchy sequence. And so you can actually think about that as just a diameter, which is the largest distance, so the supremum of the distances between all the x and y points which are in the set. So a diameter in terms of a metric D of a set S would be this supremum. So that would give you a real number as the supremum. It would tell you the largest distance in your set. Both Cauchy sequences and uniform convergence are defined in terms of these diameters tending to 0. So Cauchy sequence is, so if we have some sequence of sets like S sub m indexed by natural numbers, oh actually let me make this big again because I'm not, there we go, I'm not writing anymore. Yeah, so down here we have our diameter. If we have a sequence of sets Sn, we can talk about sort of their diameter tending to 0, which is that if we have, you know, a series of sets and we measure each of their diameters, and if that diameter tends to 0, then in terms of that metric, we can sort of think of that about that as all of our terms are getting really close together. Cauchy sequences are just some sets having their diameters tend to 0, and the sets are just all the tail terms of some sequence, where the lower bound of the index of those terms is whatever the index of the set is. Uniform convergence is also defined in terms of diameters tending to 0, except instead of having a sequence, it's just sort of a whole function. And you have a series of functions, and you want to figure out if those uniformly converge. So what's the largest diameter between all of these terms, what's the largest distance? And as it turns out, we can actually, instead of using the d function to define a diameter, we can also use the a function to define a diameter. It'll be a little different. So what we'll do is we'll define, so we have the idea of supremums for real numbers. Here all of our elements are vectors, and so we have sort of sets of sequences, but we can still think of the idea of a supremum on our set. And the way that we can think about that is we can think about that as the supremum of some set, so a supremum of some set of our real sequences, or our real vectors, or real elements with all real components. the supremum would just be pointwise. So essentially what we want to say is that the supremum, the first projection, for example, the first projection of the supremum of a set is the same as the supremum of the first projections. And likewise for the second projection and the third projection and so on. And this actually, in a precise sense, sort of gives us the smallest element that acts as an upper bound. So over here we had this notion of boundedness for our sets in terms of the precession operator. If we extend supremum to be pointwise, then the supremum of a set actually gives us the lowest bound for that set. It only works for bounded sets, of course, in which case it's infinite or undefined. But in any case, we can extend the idea of supremums to our real space like that, and then we can define diameters in the same way. So up here we define diameters in terms of the distance metric. So the diameter of a set with respect to the metric is the supremum of the distances of all the points, all the pairs of points in the set. Over here it's really similar. The diameter in terms of this a function is the supremum of the absolute differences, so a of x minus y, of all the points x and y in S. So it's super similar conceptually, except instead of getting a real number like we would get up here, we're going to get a sequence value. So this will sort of, it'll have more nuance because we have a different value on each index. But as it turns out, despite the fact that this sort of concept is a lot more bigger, as it happens, we'll have a series of sets. If we have some series of sets, if their diameters with respect to the metric function tends to 0, that also implies that the diameter with respect to the a function tends to 0, and vice versa. If the diameter measured with respect to a is tending to 0, then the diameter with respect to the metric function, the distance function, is also tending to 0. And so this sort of biconditional relationship where diameters of sets tending to 0 is equivalent is really useful. So we have this convergence where if we have it tending to 0 on each index, then actually the diameter tends to 0 and vice versa. So normally when we talk about Cauchy sequences and uniform convergence, we're saying, you know, can we have the supremum distance tend to 0? Well, actually, instead of talking about the supremum metric distance up here, we can just talk about this a function here. And we don't have to worry about anything else. If it tends to 0, if the supremum value tends to 0 on each index, then the diameter tends to 0, and we'll get our uniform convergence or our Cauchy sequence or whatever we want. And that's super useful because we are in this metric makes our space a complete metric space. That means that every Cauchy sequence converges. So if we can prove that these diameters tend to 0, then we have convergence to something. We might not know what the thing is converging to, but that's one of the ways that we can prove convergence is by proving that these diameters all tend to 0. We can prove really nice convergence, actually. One of the ways that we'll use this is if we have a uniformly convergent series of continuous functions, it turns out that the result is also a continuous function. You can also sort of upgrade that, and we'll get into this more when we use it. If you have compactly convergent continuous functions, so that means that in each compact set they converge absolutely, they converge uniformly. If you have compact convergence, then the functions also converge to a continuous function, and that happens. I forget what the conditions are, but they definitely apply here because I've used the condition. So we'll end up using that from time to time to prove. So this will help us prove convergence for really complicated objects and functions we'll be using. So actually that is all of the preliminaries. That's the first 2 pages. Do you have any questions on any of these so far? And also, again, if you do, you can stop me at any point to just sort of ask any question you have. Okay, awesome. Okay, so that is the preliminaries. So we have recap, we have our sequence space of complex numbers. We're giving it pointwise addition. We're giving all these projections to sort of talk about their different parts and indices. We're giving it a topology. We're giving it Dirichlet product. We've got we're treating it as sort of a superset of the complex numbers. In that our complex numbers are all the numbers which are just only non-zero on the first index. Those are that's sort of our extension. We've got, it's a commutative ring, it's an integral domain. We have division sometimes, which is going to be sort of complicated. Specifically, we have cancellation, is what I prefer to call it. And we have all these different properties that'll let us sort of analyze different methods of convergence and different approximations that normally we wouldn't get in a space like this. Normally in a vector space, there's lots of using of the metric a whole lot. In this space, that doesn't work out so well because we want to make approximations with a Dirichlet product, and we won't always know if that's possible with a metric, and that is why we have the a function. So we're super primed to start doing calculus with all of these objects. We have all of these tools set up for us to do approximations and comparisons and convergence and continuity and all sorts of crazy fun things. So we're have our our second section. This one is also already written and done. This is the only other section that is properly done. And the rest of them I will just have to start writing. So this section is we're going to study more of our cancellation operation. So we, as a recap, we had said that if we have some x and y, this proportional to relation means that x can be divided by y. And so we know that sometimes this is defined, sometimes it isn't. Not everything is a unit, not every non-zero element is a unit, but sometimes we still can divide things. And being able to divide things happens a lot. There are a whole lot of non-units, and we can just multiply them together to enable some cancellation, if we want. So we're going to study some of the continuity properties of cancellation. So we know that we have this cancellation operation, and we know that it's only sometimes defined, and we want to figure out, when is this, in what sense is this cancellation continuous? Is it continuous in any sense? And the answer is yes. As sort of a primer, we know that division in the complex numbers, or the real numbers if you like, is continuous so long as the denominator does not approach 0. And so actually in the complex numbers, as you approach 0 from any direction of the denominator, so long as the numerator is not also tending to 0, if the denominator is tending to 0, it'll blow up to infinity. And there's no possible way to sort of approach 0 and get something meaningful. And that's interesting because all of our non-units are sort of vertically above 0. So there's sort of a sense in which you would think, or you might think, that because of this sort of reliance on the first index, and this reliance does become very strong, because of this sort of reliance on the first index, you would think that maybe it doesn't have any continuity properties. Why should it, right? But it actually does, and they're very interesting. So first what we have to do is we have this cancellation formula, and I showed this to you actually. I showed this to you the other day while I was deciding on different notations. I shared this. So we have this is actually our cancellation function. This is our a formula, rather. So our first theorem of this section, so this is, it's a pretty short section. It's just about cancellation. For any x and y, which are in our space of numbers, our arithmetic functions, if x is proportional to y, so if x can be divided by y, then for every index n, we have this really big formula. This isn't too rough, though. We can just sort of break it down piece by piece. So we're saying we have some x and y, x can be divided by y. And we have some index n. This is another typo. We have n there and k in the other spot. Just fix that real quick. Okay, so for every index k, the kth projection of the cancellation. So this is what our formula is equal to. This is what we want to make this formula for. So whenever we cancel x and y, we're trying to calculate, on each index we have this formula. And so this formula is, to sort of break it down, we have this reciprocal here. So this is the projection of y, and the axis that we're projecting it onto is z of y. So if you remember, the z function tells us the lowest index where the input is non-zero. So we're sort of taking, when we're taking the projection on the z of y, what we're saying is, take the lowest non-zero index of y and tell us what its value is there. So that's what this whole projection here is. And we're taking the reciprocal of that, and so long as y is non-zero, and because we're saying x can be divided by y is non-zero. So because y is non-zero, this sort of calculation checks out. We do have some z of y, and it will be non-zero because that's what the z function does. It tells us some non-zero index, some index where it's non-zero, and we're going to take the reciprocal of that projection. So we're going to take the first non-zero index, and we're going to take its reciprocal, and we're going to multiply that by this whole chunk of stuff. And this whole chunk of stuff, it looks pretty arbitrary, and that's kind of because it is. We have a projection of, so here we have another zy, we're multiplying that by k, and so again, the k is the index that we're trying to figure out. There's not like a whole lot of intuition to this until you see the proof, and then it makes a little more sense. But we have this projection of x, and we're subtracting this summation. So we have some summations over a's and b's, and we have more projections. Here we have a projection of y, and then here we have a projection of x divided by y. This whole formula, it's kind of crazy. There's a lot of stuff going on. What's important, though, is that we're trying to calculate what is the kth projection of x divided by y. And in order to calculate that, we need some other things that we already know. So we, in sort of a philosophical sense, we're sort of assuming we already know what x and y are. So we can take the projections of y, we can take the projections of x, we can take projections of y again. And then here, we do have x divided by y here again, but the way that we're using it is we're taking the projection onto this a direction, this a vector, or this a basis dimension. But our summation has k being strictly less than k. A is less than k, and that's the index that we want to figure out this projection for. So this is actually an inductive formula. If we want to figure out what's the value of x divided by y, or x cancel y on each index, we can follow this formula inductively. So if we follow when k is 1, there's no a's, so all of our a's are integers. They're indices. There's no positive integer less than 1. So this sum would just be zeroed out. So the p sub 1 of this x cancel y can be calculated really easy. And then once you have that one, you can do when k is 2, you can calculate that one. And once you have the first and the second one, you can do it when k is 3, and so on and so forth. So this is sort of an inductive definition, and that's the purpose. of this formula is that it gives us this inductive definition for cancellation. The proof is, it's not too complicated. The formula is definitely a lot more complicated than the proof actually is. Essentially what we want to do, we're sort of pointing out x can be divided by y. So this is our premise up here. X is proportional to y. So that we do have some value of z where x equals y times z. So z is the fraction here. And we're just going to use this z value as sort of a placeholder because that makes the sort of working out a little nicer, just a little bit simpler. We also have to have y as non-zero. So like we observed before, z of y is finite. It's less than infinity. And we also have this projection p of z sub y is non-zero. So in order to produce this whole formula, which is what we want, this inductive way to calculate cancellation, in order to produce this formula, we're going to use the definition of Dirichlet product. So, of course, we've got this sum across divisors, that's going to come in there. We're going to take this product y times z. We're going to use, and remember, y times z, that's just x. But we're going to use this definition of product on the product y times z. And we're going to index that product at k times z of y. And then once we sort of expand out that product, that summation, we're going to solve it. So we'll end up with this crazy sum of all these projections. And we're just going to solve that summation for the kth projection of z. And again, remember, z is just x divided by y, and that's what we want. We want this kth projection of the kth projection of x divided by y. So we're just going to do just that. So we take this y times z, we project it down onto the dimension k times z of y. And using our definition of convolution, our Dirichlet product, that's a summation across these ordered divisors pairs. So all the pairs a and b, which multiply up to equal this index of our projection, which is k times z of y. And then of course we have the a projection of z and the b projection of y. We multiply those together, add them all up, and that's our product. That's a Dirichlet product. So what we're going to do is we're going to sort of expand this out a little bit. So one of the divisors of this k times z of y, so k is an integer, and k is a divisor of k times z of y. So one of our pairs will be when a is k, and of course b will be z of y. So that's one of the pairs, one of the divisor pairs. So we're going to pull out that term to the front, and that's this first term here. And you'll notice that gives us our p sub k of z. After that, what we should have up here in the top, what we should have is a not equal to k. So we're summing out across all of these divisor pairs, but we're going to have a not equal to k. But actually what we can do is we can go straight down to a strictly less than k. So after we take out the term where a is equal to k, the only thing that's left is a less than k and a greater than k. And right down here, we have this note explaining this line. The restriction of a less than k is valid because if a is greater than k, so after we take out the a equals k term, if a is greater than k, then we'll have, so our b, because a times b is equal to k times z of y, then b is equal to k times z of y divided by a. But because a is greater than k in this context, this would be less than z of y, right? Because we have k divided by something bigger than k, and then multiplied by z of y. So that would be strictly less than z of y. But if b is strictly less than z of y, then p sub b, the bth projection of y, is 0. Because that's what our z function does. It tells us the lowest index where the projection is non-zero, which means if b is less than that, then it has to be 0. Then it has to be 0. So we don't get any other terms for a greater than k. They're all zeroed out. So that allows us to just do a less than k. So we have the a equals k term, The a greater than k term all gets zeroed out, and then we have the a less than k terms, and that's what's left. So we now have this equality. We have whatever this is, doesn't matter. We have whatever this is, and then we have this thing. And the key sort of important thing here is that right here, we have our p sub k of z, and we just want to solve for that, because that's what we want our formula to be. So we just have this simple, something equals this thing times this other thing plus this third thing, and we just want to solve for this. So some simple algebra, solving later, subtract this whole summation over to the left side. That's what this subtraction is here. So we take this left side here, subtract the summation, and then we want to divide by this term, and that's exactly what we've done. And that gives us our formula. This is written in terms of z, but we just wrote z as sort of a shorthand for x divided by y. So we can just do all these replacements. So z is x divided by y, and then over here we had y times z. Well, y times z is just x, so we have x here. And then right here we had z, and that's just x divided by y as well. So this gives us, our cancellation formula. This is exactly what we wanted, and that's sort of the claim that the theorem is making. So we have this sort of crazy cancellation formula. Really, the important thing here to note is that even though we have all of these, there's a whole lot of stuff going on here. What's important is that we've solved for this cancellation inductively, and that's actually the important part here. So even though all this stuff is just crazy and wacky, and there's lots of projections and things going on, the real important thing is we have this cancellation, and we've solved a formula, an inductive formula. And it's a very nice looking inductive formula, despite how sort of crazy and wacky it is. All we have is some projections and some multiplications and some subtractions and additions. And so even though this formula is kind of crazy and has a lot of stuff going on, it's actually super useful. So our next result takes use of this. Is that we're going to consider some functions f and g. So remember, we're studying the continuity properties of cancellation, and that's why we have this cancellation formula here. If we have some topological space x, and we have functions f and g, so they map this space x over to our A space. If we restrict g is a continuous function, and the z value, so if we take z of g of any of its inputs, if that's constant and finite, then what this theorem is saying is that the function f of x convolute or product times g of x, that's continuous if and only if f of x is continuous. And that's a really strong statement, because we haven't made any restriction on this space x. We haven't made almost any restrictions. Actually, we haven't made any restrictions on f. And the only conditions we put on g is that g is a continuous function and that its z value is constant and finite. So what that means basically, other than being constant, the finite part just means it's non-zero. So as long as g is a non-zero function, so it's never zero, and also it's constant, this product f times g is continuous if and only if f is continuous. And so we can sort of think of this as, when we go from f times g over to f, that's a cancellation of g. We're canceling off the g function in order to go from f times g over to f. So the forward direction is really simple, actually. If we know that f is continuous, well, our premise is that g is continuous, so of course the product is continuous. Really, the special part is if we don't know whether or not f is continuous, and we only know that the product is continuous. That's the special part. That direction is sort of what this whole proof is. So we're going to take, by premise, we're going to suppose this f times g, the Dirichlet product f times g, is continuous. And we're going to do an induction on the indices. And what we're going to do is we're going to, by our inductive premise, we're going to assume that for every index a less than k, the projection, so if we take this function f and we compose it with this projection, so p sub a is the ath projection, So if all of these lesser projections of the f function are continuous functions, and that's sort of our premise, is that all of these lesser projections are continuous. What we're going to do is we're going to prove that given this premise, then the kth projection is also continuous, and that will give us our induction. Of course, this is vacuously true when k equals 1, and the reason that is the case is that if k is 1, there's no positive integers a less than k. Very useful. So we don't have to do a complicated base case. We get our base case for free. Is that if k is 1, then our inductive premise is automatically true. And so in order to prove this, so we take this as our premise, and we're going to prove that the kth projection is continuous. For convenience, we're going to use this m sort of placeholder number. That's going to be, that's the constant value of z of g. So one of our premises on g, so g is continuous, and also the z value is constant and finite. So we're saying let m be the constant finite value of z composed with g. So that's sort of our placeholder. And now, because we have f of x times g of x, this is proportional to g of x always. And actually that's trivial, right? Because we have this proportionality statement just means can be divided by. And because g is, we restricted it, it's always non-zero, because its z value is always finite. And of course, clearly, we just have this product right here. So the cancellation of f times g and then cancel g, that's just f again. And so we're going to actually, because we have this proportionality, and that's the condition on our, right here, that's our conditions on our cancellation formula. Because we have this proportionality statement, we're going to use the cancellation formula. So what we're going to do is we're going to cancel f times g, and we're going to cancel off g, so that'll give us f. So the cancellation is actually just f itself. So the kth projection by the cancellation formula of this f function, so just like in the cancellation formula up here, we get our reciprocal of p sub m, so that's our z is the m of g of x, and then we get this projection of f times g of k times m. So again, this is just, we're just plugging in all of our terms to our cancellation formula. And then we subtract off the sum of this projection of f and this projection of g. And so remember, this cancellation formula is inductive. This is really useful in this case because by our premise, so we've taken the premise that for each of these lesser indices, a less than k, the a projection of f is continuous function. So that's our inductive premise. Well, this whole term here, this whole summation, we have this projection of g, which is continuous. We have a projection of f times g. So we've taken by premise that f times g is continuous. We have this finite summation. We have these lesser projections here of f. So these are the ath projection of f, where a is less than k. So all of these are continuous. And then we have these projections of g. Because g is continuous, we know that these projections are continuous as well. So, and critically also, because m here is the z value of g, it's constant, and g is continuous. Hello! Because we have this m as our z of g, which is a constant, we know that this projection p, the projection of onto the mth direction of g, is always non-zero, and that means that because this function, this projection here, it's continuous and always non-zero, that means its reciprocal is also continuous. That's sort of a key property here that we can use, that this first term here is continuous, even though we're taking its reciprocal, because it's always non-zero and the g function is continuous. So we have this continuous thing times this continuous thing minus this finite sum of this product of these other continuous things, and that's all continuous. Because all of these terms, it's a finite, a product of a difference, of a finite sum, of a whole bunch of different continuous things, then the result is also continuous. But the result, this entire term here, this is just the kth projection of f of x. So what we've proven with this whole cancellation formula, because all of these different terms are all continuous, that the kth projection of f of x is also continuous. And so our inductive premise, again, recall, we assumed by premise that all the lesser indices, a less than k, would be continuous. Under that premise, we've proven that also the kth index, that's also going to be continuous, that projection. And because our integers, we are well ordered, and our base case, right, our base case is vacuously true, it's trivial. That's an induction. All of the projections, every single projection, piece of k of f, is all continuous by induction. They might not look pretty, but they'll be continuous. And because they're all continuous, because f is continuous on every projection, by the properties of our product topology, if every projection is continuous, then the function is continuous. So f of x is continuous, and that proves the theorem. So just to recap what the theorem is saying, any topological space x, any two functions mapping that topological space over to our A space, our arithmetic function space, our g function is continuous, and its z value is constant and finite. If those premises are true, then the product f times g is continuous if and only if the function f is continuous. That's super great and incredibly useful. It might not seem super useful. This sort of property is trivial actually in real numbers or complex numbers, but it's really useful for us because we didn't presume that this z value would be 1. If it was 1, then g would always be a unit, but we haven't assumed that it would always be 1. It could be anything. It could be 2 or 3 or 4, despite the fact that this cancellation can't possibly, be continuous everywhere, because we can't cancel off things when cancellation is invalid. Despite the fact that that's true, and despite the fact that division is very sort of poorly behaved, especially nearby 0, despite the fact that all of that, we still get this continuity property of cancellation under the right conditions. And so we have a whole bunch of corollaries for this. We have, our first corollary is the most fun. It's the simplest one. The reciprocal function, so the function which takes x and maps it to the inverse of x, the multiplicative inverse, is continuous over its domain. So remember, its domain is a star, the set of units. In order to prove that the reciprocal function is continuous, we can just take this theorem and we can just plug in, we just figure out what are the different values that we want to plug into this theorem. So what we can do is we can take the space x to be a star. So a star is the domain. That's the topological space. We can take f of x to be the reciprocal function. That's always defined over a star. And we can take g of x to just be the identity function x. And this will satisfy our theorem. And the reason we know that, so we have x is a topological space, f and g map x to a, g is continuous, right? So right here we have g, in this case, g is just the identity function. It's continuous, and its z value is constant and finite. That's true because over here in our a star, in our domain, if we have x inside of a star, its z value has to be 1 in order for it to be a unit. Its first index has to be non-zero. But of course, because g is just the identity map, whenever x is in a star, then g of x is also in a star. So g of x will also have a z value of 1. That's constant and finite. So by the result of this theorem, f times g is continuous if and only if f of x is continuous. But well, f of x times g of x is 1, because we have x times x inverse. That's just 1, the unit. And of course, that's constant, so it's a continuous function. And because because that's a continuous function, the product f times g is a continuous function, then f of x is a continuous function. So f of x, which is the reciprocal function, is continuous in its domain. So that's sort of a really neat proof to take this really powerful theorem and to use something that's kind of simple. In my original draft, I had proven this case sort of independently. I proved it actually, in fact, you can do this cancellation formula, sorry, not this one, the general cancellation formula, which is this one. You can just use actually the standard way to calculate the Dirichlet, inverse in sort of the convention is actually to use a formula really similar to this, except instead of z of y, you just assume, so if y happens to be a unit, you just use z of y as 1, and x is also going to be the identity 1. And so in the normal, we can actually look that up. I have it, probably, I don't have it. We can just pop it out. We're going to get, give me a sec. I'm going to go over to Dirichlet product, Dirichlet convolution, and scroll down to Dirichlet inverse. So the way that normally people are calculating this is, here we go, this terrible formula. Let me put this over on the side for you. Give me just a second. I hope you can see this. That shouldn't be open. I wasn't really prepared to actually open my browser. Hopefully you can see that a little bit. You can't. Oh gosh. Let me try again. I'll turn off this and turn on that. Okay, perfect. Okay, so the normal way to calculate Dirichlet product, they've got it right here as this summation, this crazy thing here. It's really similar. It's also an inductive definition. So they're using a little different notation than us. Instead of using projections, they're treating the objects themselves. Yeah, I fixed it. Yeah, I definitely broke it for just a second there. But yeah, so instead of treating their objects like vectors and numbers like we're doing and using projections, they just treat their objects like functions. And the conventional way to calculate Dirichlet inverse right here is to use this inductive definition. So they sum across these ordered pairs of this, they have this almost convolution, and then they multiply it by this negative reciprocal of f1. And this is almost the same formula as we have over here. They have to use, in the standard way that people do it, they have a special case where on the first index, they say the first index is the reciprocal of f1, in order so g is their inverse of f. So the first index is the reciprocal of f1, and then all the other indices are this negative reciprocal of f1 times this summation. And we have something really similar to that. We do have this negative, so we have this reciprocal of this lowest index of y, and we do have this almost convolution, except we're sort of losing the top term to get us in our inductive thing. We also have this term right here, and they don't have that in this sort of, in the conventional way that it's calculated. They don't do it like that. They do it in cases. They do the first index is this, and then the rest of the indices is this other formula. And we've managed to fit that into just, let me switch back again. We've managed to fit that into just one formula rather than two different cases. And so the way that we sort of squirreled that away is if you're doing normal cancellation, the z of y, so you'd assume x is 1, the unit, and z of y, so you'd assume y is the thing that you're dividing by. You would assume that z of y is 1. And so this piece of k, you'd end up with this projection onto the kth index of whatever x is, which in the simplified case, where we just want to take the reciprocal of y, x would just be the unit, which is e1, the first basis vector. And so this projection, the projection of e1, it'll be 1 if this index k happens to be 1, and it'll be 0 otherwise. And so that's where we get our cases from, because if we have k as 1, then we'll get this positive 1 divided by this first term, and then we'll get a less than 1. Well, that's an empty sum. And if we have higher indices, then this term would 0 out, and then this term would get negative reciprocal of this lowest index of the rest of the sum. So that's sort of how we've gotten away with only having one formula instead of the usual convention where they have two, where they treat the first index as a special case. So we've sort of gotten away with not doing it that way. Anyway, so this is our cancellation formula, and so we've proven that our cancellation is almost sort of continuous. If we have so we have our here we are, yeah, so reciprocal. The reciprocal function is continuous. Normally, the way that you would prove that was what I was trying to get to, was you would use the simplified formula, which is known, which is a little simpler than this general cancellation formula. And you would just use an induction to prove that each index is continuous, in order to prove that the reciprocal function is continuous. But here, because we've sort of done all the heavy lifting in one step, we can just sort of get away with just sort of filling in the blanks, because we know that the reciprocal function times the identity function is 1, which is a constant function, it's continuous, then the reciprocal function also has to be continuous, so long as this we're in a domain, right, where this g is where this g has a constant z value, which it will in A star. The next corollary to this this result is if we have, and so this one is actually super useful. We'll probably use this one implicitly a whole lot. If we have some non-zero value c in our space, for any given sequence, some x sub n, which is also in our space, this sequence will be convergent if and only if c times this xn sequence is convergent. And that's super useful. It seems obvious, but again, because the space that we're working in is so complicated, it's not quite as obvious as it might seem. So this is a very important result. But the proof, again, is really simple. So of course we know if the xn sequence is continuous, then naturally this c times xn will be continuous. So it's really the reverse direction, which is hard. And in order to prove this reverse direction, we'll just take these functions. So we'll take, we're going to have our space x be the extended integers. So again, we can have in our theorem, we can have our x be any topological space. So here the topological space we're using is the extended integers. Our function f will have on each integer, it'll just be x sub n. And we're going to take f of infinity to be whatever the limit value of the sequence is, if it exists. And we'll take our g function to just be the c constant function. And the way this fits into our theorem, so remember, because c is non-zero, then the z value of g will be finite. And because c is a constant, so g is a constant function, then the z value of g will be constant and finite. And of course also g is continuous. And we have So G is continuous, it has a constant and finite z value, and the product, so we have f of times g, so f of n times g of n, that is just, it's equivalent to the sequence, c times x of n, right? Because well, f of n is x of n, g is c, so their product is c times x sub n. But this sequence, by premise, if this is convergent, right? If this sequence is convergent, then its function, when considered as an extended, integer valued function, integer domain function, that'll be continuous. Actually, the only non-isolated point, so the only point of interest in the extended integers, is the infinite point when you go off to infinity. That's really the only one that's important. Yeah, so, but because we have, f of x, f times g is the sequence, if this is convergent, then it'll be continuous in n over line. If it's not convergent, it won't be continuous. So this sequence is convergent if and only if the product f times g is continuous, and the product f times g will be continuous if and only if f is continuous, because that's our theorem. But if f is continuous, if this xn series with this limit is continuous, then it has a limit. The limit exists. And that's sort of the result. So this sequence will be convergent if and only if this other sequence is convergent. And that's super useful to us, is that we can sort of get away with this. The way that we'll end up using that a lot is this lets us have limits be linear. So in real numbers or complex numbers, if you're ever doing limits and you have some constant, like you have the limit of like 2 times some function, you can just factor that 2 straight out of the limit normally. In this context, it's not so clear, it's not immediately obvious why that should be possible, but we've shown that in fact it is possible, that you can just pull out any value that you want from the term, and it'll end up being continuous, and that the limit will the limit will exist if and only if whether or not you pull out the constant or not, it'll still be continuous, and it'll have the same actual result. The next one is sort of vaguely related to that. So the next 2 results, actually the next 2 corollaries, are based on these subspaces. So we're going to take some constant c in our space A, and we're going to take this set of values where we just take all the things in A and we multiply them through by c. So the set of c times x, such that x is one of our sequences in A. And our corollary now is that this is a closed set. And the proof for this is super straightforward. In the case c is 0, it's trivial, because if c is 0, then this will just be this set containing 0 and nothing else, which is super, basic. In all of the other cases, though, for any other value of c, so if c is non-zero, we can take, so in order to prove that this is a closed set, we will just prove that it's closed under sequential limits. So take any convergent sequence, so c sub xn, because c sub xn is convergent, so in our c times a set, because by premise this sequence is convergent, so take any convergent sequence where the sequence itself is in our set. It doesn't have to converge to the set, but just any sequence which will converge. Because this is convergent, x sub n is also convergent, and that's by our previous corollary. This sequence x sub n is convergent if and only if c times x sub n is convergent. So if c times x sub n is convergent, then the x sub n is convergent. Because the x sub n is convergent, then there's some limit. We have some limit x sub n limits to L, so some L inside of our space A. By continuity of the product, because x sub n limits to L, then c times x sub n limits to c times l, but c times l is just in the space c times a. So the limit of our sequence, c times x sub n, is also in c times a. Since a is a sequential space, so it's defined in terms of its sequential limits, and we've just proven, so c times a is sequentially closed, so all the sequential limits will converge inside of a, then c times a is a closed set in our topology. So these are really nice, and we will use this in maybe an unexpected place. Eventually we're going to get to defining the derivatives of functions in our space. We'll have functions from our space of arithmetic functions, to back into itself. And we'll define derivatives of those functions in the same way that you would define derivatives of complex functions or other more complicated objects or real functions. We're going to define derivatives. In order to define derivatives, we have to talk about division. And actually that's why we have this little note down here. Whenever c is non-zero, this set of c times a, this set, which is c times x, such that x is in a, equivalently, this is also the set of x in a, such that x is proportional to c. That is, this set of x which can be divided by c reliably. So these are really important. So knowing that this is a closed set means that if we have some series and we can divide all those things by the same number, then the limit can also be divided by that thing, whatever that thing happens to be. And we will use that. It's very useful to us. Okay, so the last corollary that we have for our theorem about the continuity of cancellation is if we take any value c, which is non-zero, so any non-zero c value, this mapping, which maps x over to c times x, this is a homeomorphism for the space A over to the space c times a. And so that means it is a continuous bijection, and its inverse function is also continuous. And the way that we prove that is we'll take the space x as being c times a, so this is our c times a set. So our space x is c times a, and so we're deploying our theorem again. Our function f will be x divided by c. So of course, if our space x is c times a, our function f, we can always divide everything in here by c. So our function f of x is just x divided by c, which is always valid. And our function g of x is just the c constant. So our product f of x times g of x, this gives us x, right? Because we have f of x is x divided by c, g of x is c, their product will just be x. So since this product is x, that's continuous. We also have, since g is just a constant, it's actually a non-zero constant. G is continuous, its z value is constant, and its z value is the same as that of c, and that's finite. So g is continuous, has a constant finite z value, and this product f of x times g of x is also x, which is continuous. By our theorem, f of x times g of x is continuous if and only if f of x is continuous, so f of x is continuous. So remember, our f of x function was just x divided by c, and its inverse function is c times x, right? So if we have our f inverse function, if we have f inverse, so c times x, c times something, f inverse of f of x, c times x divided by c, that'll give us x, and the vice versa if we go the other way. If we have f of f inverse, that's f inverse divided by c, but f inverse is just c times x, and then we divide by c, and that gives us x. So that's a continuous function, because f is a continuous function, that's from here, and its inverse function is just a product, that's continuous. So f is a bicontinuous bijection, and that makes it a homeomorphism. Also, as a note, f inverse, which is this mapping. F inverse is just the mapping c times x. that's also homeomorphism. And also, just sort of as a bonus, this homeomorphism is also linear, which is very interesting. And that's our last corollary for now. That's the last sort of result we have. Do you have any questions so far? I know it's a lot to take in. Over 9,000. I love it. Okay, great. Yeah, so so we have all of these things. We have this cancellation. Hello. Oh, it's Josh. So we have all of these things. We have our integral domain. It extends the complex numbers. We can sometimes divide things, and even though this division is really weird and multidimensional, sometimes it just is continuous. It just happens to sometimes be continuous, which is very nice. That's the whole shebang, I guess. That's sort of what I have in this draft for now. I have some other things that I'm working on, importing from my previous drafts. There's a whole bunch of stuff that's sort of lying around. So I think that's, in terms of the presentation portion, that's sort of all I have for now. Over time, I will be updating this draft more and more with more results. This will be updated from my second draft, which is really long. We'll be basically taking all of these ideas from the second draft, summarizing them much more succinctly, with slightly better notation, and hopefully with more references in the end, so that I don't have to explain some things that are already known. But there's a lot of stuff that we have to sort of take over here. Nice, very good. Yes. That's exciting. So that's all I have right now. I think also it's time for dinner. Yeah. Yes. That's good to know. I will probably be doing this again, not quite on the presentation quality that we've done it today, but maybe just general editing and updates and things like that. So there'll be a lot less exposition and more just working out. So like today, we worked out this proof, that we have this little inequality here. It'll be more of things like this, so we'll have more stuff in the future that'll be working out proofs and doing stuff like this. Yeah, it is dinner time. Yes, bread time. So so in the future, I'm not sure when, probably tomorrow actually for me, and probably most days I'll be working on this, just trying to update the draft and add more stuff. And less y position? I don't think I understand what you're asking. Oh my gosh, I get it. X position, Y position, Z position. Yes, you'll actually have more Y position in the future. So please look forward to that, to more Y position. Yes. Yeah, less X position, more Y position. So we're moving up and to the left. Yeah, so I will see you all next time when we move up and to the left. Thanks for coming and listening. And yeah, so next time we'll be doing more proofs and less exposition. And okay, so bye everyone. Have a nice night and eat dinner and stuff. Yeah.